Okay.
Start then.
I'd like to thank my co-organizers, Aleka and Olga, for doing a truly spectacular job in organizing our little colloquia series. In the spring, I'll be bringing in some outside speakers from around the area. We do miss, of course, getting together because one of the best parts about getting together is that our wonderful colleague Behzad Jalali would feed us and treat us all like kings. And so we always had speakers wanting to come back to AU Colloquia because of how well they were treated. But and in that spirit, I am organizing, and I've been working on this for a while, a group of local harmonic analysts. And we are going to have a conference this Saturday. It's called the DFT, which is a play on words, discrete Fourier transform to most of you. But on Saturday, it's going to be called the District Fourier Talks. This is related to a series of talks that are given at the University of Maryland. And let me share the screen. And as you can see, according to my button, you're all taking a look at this. There is our beautiful Capitol dome morphing into a sync function, a radial sync function. This is something I designed for a conference, the SAMHSA 215 conference, and I now can use it for the DFT conferences. So our schedule starts at 8:45. Our dean, Max Friedman, will give a talk then. At 9, we have Professor Balan from the University of Maryland. At 11, we have Professor Benedetto from the University of Maryland. And from 2 to 3, we have Dr. Chang from Georgetown. There's a session from 11 to 12 featuring myself, Michael Robinson, and a colleague from Colgate, sampling and differential geometry in Lie groups. There's a session organized by Nate Strawn over at Georgetown. He's a co-organizer of the conference on something called frame theory, and that's a generalization of orthonormal bases. And that looks like a great session. But I was fortunate enough to be able to organize a AU harmonic analysis all-star session. And that's our last session before we open up beverages. So Zois, I trust you have your beverages ready for after your talk. One of the speakers is Professor Boukovalis. We have Art Shapiro going to talk about his illusions in terms of harmonic analysis. We have Dr. Michael Barone talking to us about change point detection and harmonic analysis in time series. And we have also Dr. Nolan talking about LP spaces, alpha stable, and Green's functions. Pretty impressive talk. And Dr. Boukovalis is going to be talking about machine learning, which also there's a talk on machine learning, Zois, earlier in the day, Professor Murphy from Tufts. You might want to see that one. So with that, I will turn the floor back over to Aleka. Thank her for doing an incredible job of organizing speakers. And I am looking forward to today's presentation. So thank you.
Thank you very much, Steve. And again, thank you for organizing this conference on Saturday. So I'm looking forward to it. And now I would like to introduce today's speaker, Yuri Levin-Schwartz. Yuri received a BS in physics and a BA in mathematics from Brandeis University in 2012. His doctoral work is in electrical engineering, and he did this work at the University of Maryland, Baltimore County. His research was focused on machine learning methods on neuroimaging data. Currently, he is a postdoctoral research fellow in the Department of Environmental Medicine and Public Health in the Icahn University of Medicine at Mount Sinai. His research focuses on the effects of environment mixtures on neurodevelopment. Yuri, you can start.
Thank you, Aleka and Zois and Olga, everyone, for, I would say, for coming, but I guess thank you for tuning in, I guess is more appropriate these days. But yeah, thank you for tuning in. Let me see if I can figure out. Okay. So can everyone see my screen? Maybe just
Yes, we can.
okay. All right, so as like I said, today I'm going to be talking about machine learning and how we can use it to improve estimates of environmental exposures. So a brief outline of the talk. So I'll begin with the background, sort of try to answer some questions like, how do you measure environmental exposures? How do you measure their effects on human health? What are some issues with, the traditional approaches? And how can we improve upon these limitations? Then I'll talk about sort of the how of, how do you improve, what models do you use? How do you make them robust? What are these techniques that you can improve upon the traditional analyses? Then, discuss some results from two recently published manuscripts, as well as future conclusions, future directions. What did we learn? What can we do next? So start with the background. So I guess the first question is, how do you determine if an environmental exposure has negative health effects, right? So you'll see in the news, you'll see in like journal papers, there's like aluminum affects the brain, air pollution kills people in India, lead is bad for the brain, methylmercury is bad for you, arsenic, and so on. And so fundamentally, right, the way we determine this, the connection between an exposure and an outcome is just through, we almost always do it through correlations, right? So we have a measure of exposure on one side, a measure of some outcome of interest on the other, and we just, look at their correlations. Sort of oversimplification, but, fundamentally, this is the concept, right? And if you have, if high exposure tends to be related to, lower, let's say, IQ, right? Then you're going to say, okay, well, maybe there's something going on here. There's some relationship between, these two things, right? So, right, we look at the correlation between our level of exposure and the level of outcome, right? And what you want to do is control for, remove the effect of, confounding or nuisance variables, right? So, there could be other things that could explain the connection between A and B, right? And you want to remove those effects when you're trying to establish, does A affect B? So for example, right, if your question is, does some, construct representing the home environment affect children's performance in school, right? There are other things that can affect both the, your home environment and your performance, right? You have the region that you're from, if I'm doing a multi-country study, right, I'd probably want to consider what countries are involved. Things like parental education, race, socioeconomic status, these are things that can affect both your exposure and your outcome, and you want to sort of try to account for as many of these as you can. And, there's sort of a problem here, right? One is causality, right? So correlation does not imply causation, right? You've established that A and B are connected, but you don't know if A causes B, right? B could cause A or C could cause A and B. You don't know. You could have residual confounding, right? There could be things in your model there are things that you haven't accounted for in your model that are really sort of describing part of the connection between your exposure and your outcome. Then the question is your outcome appropriate? So if you're interested in, brain health or cognition or something like that, then you don't want to be using some measure that isn't really getting at cognition. So for example, you wouldn't use blood pressure. Or if you're interested in children's IQ, right, you need to have a good measure of child IQ. So it's very hard to assess something like verbal intelligence in an infant. How do you assess that? So you always want to make sure that your outcome is appropriate and is sort of getting at what you're trying to measure. And then sort of the one issue that is sort of the main focus of my talk today is, how do you quantify someone's level of exposure, right? How do you get an accurate measure of exposure. And traditionally in epidemiological studies, we don't have access to, sort of the ground truth, right? In animal models, you can give them specific quantity, you can give your mice specific quantities of lead. And then you say, okay, I know exactly how much lead someone's getting. But if I were to, try to figure out how much lead a human being is getting, right? I don't have access to the dosing information. So what I have to do is rely on what we call biomarkers of exposure. These are surrogate measures of exposure because we don't have access to the ground truth of what the level of exposure is. So we have to sort of try to estimate it based on some other information that we have. And basically what it is, if we have a person, we can take various media or biomarkers, with hair, saliva, blood, urine, and measure, the chemical of interest, or a metabolite. So we could, measure blood, lead in someone's blood. And, then sort of our assumption is, okay, well, if someone has higher blood lead, then that means that they have higher levels of exposure to blood, right? We're building this connection, or higher urine lead means that they have higher exposure to lead. And generally, we only use a single biomarker. We'll only measure someone's level of exposure using one of these biomarkers. And the issue is that depending on the medium that you use, whether you use blood or hair or urine, your ordinal ranking of subjects is going to change, right? So your person with the highest blood lead may not have the highest level of urine lead. And they may not, the person with the lowest level of urine lead may not have the lowest level of blood lead, right? So this is an issue because if you're trying to establish, based on correlations, the connection between an exposure on one hand and an outcome on the other, right? You want your sort of the exposure level not to change depending on the medium that you have, because that'll give you different answers in terms of what the effect of the exposure is on the outcome. And so there exist some chemicals for which we have preferred biomarkers. So for example, lead, you can measure it in, generally it's advised to measure it in bone or blood. So for example, doctors, when they make recommendations about whether someone has reached a level of lead exposure sufficient to be chelated, where they basically take your blood out and try to clean it from all the lead, right? They make that recommendation based on your blood level, your blood lead level. And similarly, cadmium, urine's preferred biomarker for cadmium, methylmercury is in hair. But some chemicals, especially those that we're starting to become more interested in recently, don't have this sort of the established literature, determining what the sort of optimal biomarkers are. And now, especially in recent times, as we're, our ability to measure what people are exposed to increases, and actually, the number of chemicals in the environment is increasing, it becomes sort of increasingly of interest to, sort of determine what, how to measure their effects on human health. And so, for example, manganese and chromium, in sort of the last 10 years or so have become increasingly of interest to, see their effects on the human body. And, but they don't have established biomarkers. We don't really have sort of, a good way to get at what manganese exposure is. And so there's sort of maybe a fundamental issue here, like why do your sort of levels of the metal and your sort of your measurements of exposure, why do they change by your biomarker? And so part of it is, from the way that a human sort of interacts with a chemical, right? So, it's absorbed, it's, it goes either through blood or lymph, you know, moves throughout your body, is processed by different organs, you know, is metabolized, maybe is not metabolized, and then is finally eliminated. Overall, you're capturing a very small piece of it with a single biomarker, right? So, you know, with blood, you're just getting, you know, this snapshot of distribution. With urine, right, you're just getting a little snapshot about elimination. There's each biomarker is sort of capturing a different piece of this. And it's also, there's another issue where it doesn't, this whole process occurs not, you know, immediately. It can take, you know, it can take a while, you know, for example, for lead, right? It can take decades for the lead that you ingest as a child to be sort of released from your body. And so, you know, but on the other hand, certain things like PCBs and, you know, certain pesticides are almost immediately excreted. You know, 95% or more are just almost, it like goes through your body, causes damage, but, you know, so there's sort of this issue of temporality incorporated in here. And so, you know, by, you know, only focusing on one small aspect of the overall toxicokinetics, sort of the, how this whole system is operating, you're sort of getting a very limited view about what's going on. And also, a thing that makes it more complicated is that the toxicokinetics differ based on what chemical you're interested in studying. So for example, right, the toxicokinetics for lead, you know, it's much more long lasting in your body than something like cadmium or PCBs, right? You know, so this is sort of part of the reason why you have different preferred biomarkers for exposure for different chemicals, because, right, they're sort of going through your body in different ways. To add another layer to this, right, humans are exposed to thousands and thousands of chemicals a day, you know, through the food that you eat, cosmetics that we use, medicines, you know, maybe there's occupational exposures depending on what you do. You know, you're exposed to many thousands of things. And so, you know, the traditional study of, you know, one exposure, one outcome isn't quite capturing what's really going on in your life. So for example, right, if you have some exposure A that you see is related to some outcome B, right, there's, you know, you have some connection there, okay. But if you find that you have some other exposure that's correlated with your, you know, the exposure that you were interested in, right, then it's a question of, okay, well, is this other exposure correlated with your outcome? Because if it is, then when you are focusing on this link between A and B, you're sort of combining the effect of C on B together in with it. So, you know, if C and A are both, you know, if the direction of their relationship is both, you know, in the same direction, you're magnifying the effect of A because you're incorporating part of C. Or if, you know, C is, you know, positively related, it, you know, makes B go up, and C is negatively related to B, you know, it makes it go down. You're sort of canceling out the directionality. So you're, you know, you're not going to see any effect of A on B when there actually is one. You're just, the issue is that your measure of exposure is sort of combining C and A. And so what you really want to start getting at is, okay, well, what we want to see is this sort of the gestalt, right? You want to see the effect of C and A on B. You want to see their effect together, because that way you can start to try to, you know, quantify both the effect of C and B and the effect of A and B together, and also see, okay, well, maybe their effects add just not, you know, not additively, it could be multiplicative. You know, maybe it really, you know, getting one is fine, getting the other is okay, but getting both really is bad for you. You know, we don't know. And so you'd want to be investigating this. But then the question becomes, okay, well, if the toxicokinetics are different for all of the metals, for all of chemicals, right? How do you determine a good biomarker for mixtures of chemicals, right? If they're, you're going to have to do this trade-off, right, between a good measure of exposure for one and a good measure of exposure for the other. And right, yeah, they're not going to align. And so what's going on right now? So right now, there seems to be there's a little bit of bias in the literature. And to clarify, let me sort of explain what we have in this table. So the rows are different media, different biomarkers: blood, hair, saliva, nails, urine, and each column are different metals: cadmium, arsenic, methyl mercury. And these elements are the number of papers, published papers, that are looking at mixtures of cadmium and lead. And then this is sort of the biomarkers that they're using. So for example, there's 45 papers that are looking at cadmium lead mixtures using blood measures for both cadmium and lead. So for arsenic, 27, methyl mercury, 33. I've highlighted in green the preferred biomarkers for these three metals. So cadmium and arsenic, urine is the preferred biomarker, methyl mercury is hair. So what you can see is that there's way more blood papers using blood than there is using the preferred biomarkers for these other metals. And so blood isn't the preferred biomarker. So what does that mean? Well, that means that you're sort of inaccurately estimating exposure for these three metals or any other metals that aren't preferred to be measured in blood. In order to get a very good estimate for lead, right? So the issue is, right, if we have inaccurate measures of exposure for the other metals, the metals aside from lead, you may be underestimating or incorrectly estimating their effects, right? If you don't have a good estimate, you can't really establish how much it's affecting your outcome. If you don't know, you can't. If you don't know how high someone's level is, you can't tell them how much it affects their the outcome that you're interested in, right? And so then the question is, okay, well, let's say we had a mixture of just these four metals. Okay, well, what single medium could we use that would be preferred for lead, cadmium, arsenic, and methyl mercury? And you see that there is no single one, right? Blood is for lead, but not for the other three. Cadmium and arsenic, like urine, but that doesn't work for the other two, methyl mercury and hair. It doesn't matter what you pick, you're always going to be preferring one, giving preference to one or two of these metals to sort of the detriment of your estimation of the effects of the other ones. And, this is just four chemicals, right? This isn't even getting close to sort of the thousands of chemicals that you're exposed to every day. So like, how can we start trying to figure out, what the true impact of environmental exposures are on human health if, we can't even, it's going to be hard for us to estimate even, exposure for even four, right? So what's the solution? Well, so the solution that we've come up with is, to realize that, okay, individually hair, saliva, blood, urine, nails, they may not fully capture the entire toxicokinetics of the chemical under study, right? Maybe they're just getting snapshots, but they're all giving you some amount of information, right? And depending on the medium, it may be higher, it may be lower, depends on the medium and the chemical that you're studying, but they're all giving you something. And so rather than dealing with these separately, why don't we try to combine the complementary information that we're getting about exposure, derive some sort of integrated measure of exposure, which we refer to as a multimedia marker, and use that as your measure of exposure, right? And so our hypothesis is that by using all exposure information from all available biomarkers, we expect to reduce the error, to somewhat reduce error in the estimation of exposure, right? By combining more information about people's level of exposure, you'd expect to, on average, get a more accurate estimate of exposure. Okay, so how do we do this? So what we've applied are what are known as traditional mixtures approaches, right? So the idea is you want to understand the effects of multiple chemicals on an outcome of interest, right? And many of these techniques you'll probably recognize. We can group them into two groups. One are sort of unsupervised learning techniques, principal component analysis, ICA, independent component analysis, non-negative matrix factorization, right? Where we're going to take sort of all of our exposure biomarker data and we're going to derive some set of factors based on some properties of the data, incorporating either the correlation information, higher order dependence, we're going to derive some set of factors. But one piece of information we're not going to use is the outcome that we're interested in. The other set of techniques are supervised learning techniques, right? Random forest, weighted quantile sum regression, supervised learning, supervised PCA, ICA, right? They're still going to derive factors, but the factors are going to be derived using some information from your outcome to derive these factors. I'll get into this a little bit more later in the talk. But one of the key things about all of these techniques is that you can use them to determine the biomarkers, the media that are going to be the largest contributors to your multimedia biomarkers. And so this, you allow them to determine the, sort of the biomarkers that are most informative, which is useful because there are many chemicals, as I said, that don't have a preferred biomarker. So we can see, we're able to derive useful information about, okay, what are the useful biomarkers to measure exposure for novel chemicals? So in this talk, I'm going to focus on three methods: independent component analysis, non-negative matrix factorization, as well as one supervised learning technique, weighted quantile sum regression. Independent component analysis, it's a unsupervised matrix factorization method where if we were to take our observation matrix, the data from all of our subjects, all of our biomarkers, and we're going to arrange it such that 1 to n is the number of subjects, 1 to v is the number of biomarkers. We're going to decompose it into the product of two matrices by assuming that we have some statistically independent latent sources. And we're going to try to derive factors such that they maximize the statistical independence between all of them, right? And so if we use this framework, then the rows of S therefore determine the contribution of each media to the multimedia biomarker. And we can use this information to determine sort of which media are sort of most informative in terms of contributing to the multimedia biomarker. Another technique that we use is non-negative matrix factorization. So this is, again, a unsupervised matrix factorization technique where we're going to take our observed matrix and model it as the product of two matrices again, but such that no factor or no component of any of these two matrices is negative. And this is actually a reasonable assumption in the context of trying to estimate someone's level of exposure, right? Because you can't have a negative level of exposure, right? The lowest you can have is no exposure, which is 0. And then it can be positive. But, so it's a reasonable assumption in this context. Additionally, we always assume that the rank of your feature and coefficient matrix is less than the original data. And then we can, again, using the formulation of if each of our rows is a different subject and each column is a different exposure biomarker, then these rows are the rows of our H matrix are going to determine the contribution of each of the media to the multimedia biomarker. So then the final technique I'll talk about today is known as weighted quantile sum regression. So this is a supervised learning technique. So we're going to incorporate information about the outcome in estimating our feature. And so the way it works is it's basically trying to model the body burden of a set of quantiled exposures, these QM. So we're going to quantile, put them in deciles, quartiles, quintiles, whatever, but we're going to put each person, the measure of exposure from each person into quantiles, and then we're going to estimate weights under, I guess, 3 criteria. 1 is they have to be non-negative. 2 is the sum of the weights have to equal 1. And 3 is we want these weights to be estimated such that the combination of your quantiles with your weights is going to have maximum association with your outcome of interest. And what we're going to do is basically repeatedly estimate weights based on repeated bootstrap data sets. And we're going to then, weigh the weights from each bootstrap data set based on their ability to sort of highlight this association, right? So based on the chi-squared from each of the models. The stronger this weight is in terms of estimating the effects of sort of the combination of biomarkers on the outcome, the higher we're going to give it in this sort of weighted average scheme. And then we can use these weights, because they're applied to each of the biomarkers individually, to determine the contribution of different media to our multimedia biomarker. And so here are some things that we've started doing just to try to get at robustness. So reproducibility and generalizability are key for our results to be, 1, interpretable, but also sort of useful for other people. We're trying to make recommendations about what to, if we're analyzing novel chemicals, what we're going to try to derive is what are the media that are most useful for measuring exposure. So, you want to give people some indication that, okay, well, we're fairly confident that you can find that these media are good measures of exposure for you when you measure chemical X, right? So what we've started doing is, to reduce chances of overgeneralization, we split the data into testing and training, derive the multimedia biomarkers using the training data, and then whenever we report associations with the outcome, we use the testing data. We use the data from the testing set. And this enables us to sort of somewhat reduce the risk of overfitting, especially in in the supervised techniques, because you're not then sort of mixing your testing and training data. But in order for everything to be consistent, we're using the same data for each of our methods. So you're not, measuring your association using fewer samples or more samples based on the method that you're using. So let me the focus of my research is understanding the effects of metal exposure on child brain health. So the measure of intelligence that we use, and that's been commonly used in the literature to measure intelligence, is what's known as the WISC. It's composed of 2 different domains, and you can derive summary scores from each of these domains. So for example, the first domain measures like verbal intelligence. It's composed of 5 subtests, and you can derive a summary score that's known as verbal IQ from these 5 subtests. And as I said, it measures their verbal intelligence. So for example, one of the things that people could be asked to do is like describe similarities of differences between apples and oranges, or describe as many synonyms for this word as you can, and so on, right? But it sort of is measuring your verbal intelligence. To contrast this, the other 5 tests in the standard WISC measure performance or nonverbal intelligence. So this is more problem solving, critical thinking, so one thing that participants could be asked to do is, okay, given these 3 panels, what is, the fourth panel that you could fill it in such that these create a logical sequence. What you can also derive is what's known as total IQ, which is just the sum of the verbal IQ and the total and the performance IQ. And those are sort of the 3 metrics that we're going to be focusing on. And just a little bit about the cohort that I used in the study. The cohort is the public health impacts of manganese exposure, or FIME cohort. It's based in the northern Italian steel production region, and it consists of 3 sites. My Italian is terrible, so I'm not going to try to pronounce them, but the 3 sites are, one has recent admission from a ferromanganese smelter, which was closed in 2017. One has more historical exposure from a ferromanganese smelter that was closed in 2001. And the third has no past or present emissions. So it's a control region. This is a cross-sectional study, so this means that the participants only came in once, and we have 1 measure of exposure, 1 measure, or 1 set of measures of exposure, 1 set of measures of the different outcomes that we're interested in. We have data from around 720 adolescents between the ages of 10 and 14 years. And there are multiple metals that were measured in multiple media. So blood, hair, nails, saliva, and urine, right? Which is good. We have sort of a spread of different aspects of their, of the sort of toxicokinetic, different measures of each metal's toxicokinetics. So results. So just briefly, we have a complete data from around 260 participants. It's an even split between men and women. There are about, the average age of the participants is around 12 years. So the first result is we applied this MMB principle. So we wanted to select a test case that would really highlight the utility of an MMB and use it for sort of an established environmental effect. So what we're looking at is lead and intelligence, right? There's a very strong evidence base, decades, almost, I think actually like a century of published literature highlighting the connection between lead exposure and intelligence. And so we sort of selected this as a test case, to sort of prove that you actually can, maybe you can do better than the sort of the gold standard measure of lead exposure, which is blood lead. So what we're looking at here is the, so the y-axis here is your beta coefficient, 95% confidence interval. So this is highlighting the connection between lead and total IQ in the WISC, and your 95% confidence intervals, right? If it intersects 0, then you can't. What you would say is, there's not sufficient evidence at an alpha of 0.05 for us to say that there is an association between lead and IQ. And so what I am showing here is what it is different measures of lead. So these first 4 are measures of lead from individual biomarkers, and then these next 4 are individual measures of lead from multimedia biomarkers. This equal weight is, we're interested in seeing, okay, well, maybe it's not, the algorithms aren't really doing anything important. Maybe it's just, if we were to take the average, a simple average, then that would be sort of an equally competitive approach. And so that's this equal weight multimedia biomarker. And so what we see is actually, individually, none of these biomarkers are, there's sufficient evidence to sort of link their, the effects of lead on intelligence. We also see it's insignificant for the equal weight multimedia biomarker. But we have consistent and significant evidence that these measures of lead exposure from these different multimedia biomarkers are all associated with total IQ. And I should mention that these, the 95% confidence intervals are scaled such that we are comparing we are taking into account, your family-wise error rate. So it's basically like a Bonferroni correction for the fact that we're doing really 8 different tests. But, we see sort of strong evidence, fairly strong evidence for an effect of lead on IQ using the multimedia biomarkers, but not using any of the individual media, which is interesting because even blood lead, which is again the gold standard, wasn't picking up these effects, but we could pick it up using sort of this approach. And as I said, we can also derive weights such that they highlight the contribution of each media or each medium to the multimedia biomarker. So here on the y-axis, I'm showing the contribution, each of the different media that are contributing to this multimedia biomarker. And here I'm showing their contributions. And what you can see is that blood is the #1 contributor to all of the multimedia biomarkers, except the equal weight one, but we can leave that aside for right now because it's not informative and wasn't significant. So that indicates that each of these methods is saying that, okay, well, blood is really the strongest contributor. It's the most informative for each of the multimedia biomarkers. But, there are other weights associated with other media. And the fact that you're seeing significance, here where you weren't seeing it here is showing that there is added utility in driving some additional information from those other media. They are adding to the overall level of, or to your measure, to building a better measure of lead exposure, even though blood is sort of contributing the most to the effect. So next we looked at, okay, well, let's sort of extend this from a single 1 metal study to multiple metals. And, we started out slow, so we just considered 2 metals, lead and manganese. And what we looked at is, so this is again looking at, beta coefficients, 95% confidence intervals, highlighting the association between this mixture of lead and manganese and the WISC, verbal IQ. And so what you can see is we have a bunch of individual media and then our MMB approach. And for the MMB here, we only used the WQS MMB, but we could have done it for other ones. This, just to save on space, we only considered one approach. And what you can see is that we have significant effects for blood, hair, saliva, as well as the MMB. The MMB is again the most robust in terms of 95% confidence intervals being furthest away from 0. So, right, lowest p-value and stuff like that. But, other measures of lead and manganese in other media are also delivering significant effects. So what we can look at is the contribution of each of these metals, each, lead or manganese to the overall mixture effect. So what I want to draw attention to is if we look at blood and we look at saliva, both have significant effects of the significant lead manganese mixture effects. But if you look at the contribution of each of the metals to the overall effect, in saliva, it's 95% or so manganese, 5% lead, whereas in blood, it's, the other way around. So it's like 95% lead, 5% manganese. And so that means that, okay, if you had only used one of these 2 media to measure your mixture effect, you'd get, very different conclusions in terms of what's the main driver of the effect, right? If you had used saliva, you would say, oh, it's all manganese. It's, lead isn't really doing anything. If you had used blood, you would be, saying, okay, it's all blood or it's all lead. It's, manganese isn't really contributing anything. And so what we also see is that, our MMB approach, which again is sort of the most robust in terms of detecting the association between the mixture effect and IQ, it has a more sort of even distribution, which we would think, and is more sort of, is therefore sort of more stable in terms of, and more reasonable in terms of the sort of relative contributions of these different metals. And so we would sort of we would prefer to use something like that for interpretation. So to conclude, individual exposure biomarkers may provide incomplete information on the level of exposure, and by jointly utilizing multiple exposure biomarkers, we can provide more accurate estimates of exposure response relationships than just using an individual medium. And future work, so one thing that I've sort of have skipped over, but is nonlinear methods. So all of the methods I'm highlighting here have sort of basically are doing sort of like a linear combination of these different media to sort of derive your multimedia biomarker, but that sort of doesn't really get at the sort of the complex toxicokinetics that we sort of know many of these chemicals have. So we want to sort of logical extension is to use nonlinear models to sort of try to get at these nonlinear relationships, as well as extending into more complex mixtures, as well as additional outcomes. There's many people I want to thank very briefly. Chris Jennings, Bob Wright, Megan Horton at Mount Sinai, Don Smith at UCSC, Birgit Klaus-Henn at Boston University, Donatella Placidi at the University of Brescia, as well as Brent Kuhl at Harvard. And then, of course, all of Thank you.
Okay. Thank you very much, Yuri.
Of course.
Any questions for the speaker?
Well, I don't necessarily have a question, but this is an observation for both Yuri and Zeus, that when I was looking at the ICA analysis and the NMF analysis, I was immediately reminded of what is a hot topic in harmonic analysis right now, and that's finite frame theory. So we're doing a lot of those exact same computations in finite frame theory, those decompositions that you pointed out. And the other thing is, for the NMFs, there's wonderful theory by Solomon Bachner on, non-negative or positive measures and its relationship to harmonic analysis. So I would recommend looking into that literature, and I can send Zeus a lot of my connections with that, and then he can forward that to you. So thank you. But that was an excellent talk. Thank you.
Oh, thank you. Yeah, I really appreciate it. Yeah, there's, I feel like many people in many different fields have sort of come across similar problems. So, it would always be good to see sort of what's out there in terms of what people have done before and what, we can expand upon. Yeah, thank you.
Yeah, these are incredibly powerful computational tools that we use. And you'd be amazed at the frame theory people. I'm really good buddies with a lot of them, and they are doing some really spectacular computations in terms of decomposing the matrices in terms of, bases and generalized bases of frames. And I think a lot of this work would be applicable. So.
Yeah, it sounds definitely applicable. I mean, ICA, NMF, they're just, decomposition methods. You're just coming up with, bases or factors or whatever you want to call them, in using different assumptions in terms of the construction of the bases. So yeah, if there's other approaches, I'd love to see it. Yeah, thank you.
Excellent, thank you.
Thank you very much. Any other questions for the speaker? Okay, no more questions.
Hi, sorry, I actually do have a question. I I just want to say thank you. It was a really interesting talk, and particularly apropos for my work, where we look at a lot of human health effects because of blood lead levels. And we've been sort of looking into using machine learning to try to extrapolate from the data that we do have. And as we're sort of learning our way through this process, one question I do have is about the statements and maybe limitations to statements that you can make about a certain sample or population. That is to say, we have a pool of data and we sort of use a machine learning extrapolation to sort of provide a particular sample's potential exposure or potential blood lead levels. But then trying to sort of extrapolate that, let's say we want to take these blood levels to predict IQ changes. And it becomes very apparent that you sort of have this compiling bias and compiling error as you sort of have machine learning's predictability error, and then you have a sort of standard deviation for what you've now generated for the population. Do you have any sort of advice on how one might sort of look to use this sort of machine learning predictions to sort of make maybe more broader population level predictions, if I've made myself clear?
Well, let me try to answer it, and then if I haven't quite got it, please let me know. I mean, I think that, one thing is that sort of the critical thing to me that I keep running into repeatedly, both in my graduate work and here, are sort of issues of overgeneralization, right? Overfitting, that you're sort of making, you're making sort of too much, too broad statements in terms of, what you think you can do based on sort of the fact, based on the samples that you have. And so that's why I think that, one of the things that's useful is, sort of just, the simple old, testing and training, which I think is, very important, just to make sure that you're a little bit more robust. And then another thing is that there are multiple, I didn't get into this, but if you have other cohorts or other data sets that you can use to sort of look at really just generalization, like how well do sort of my models generalize to a different cohort that's sort of, similar demographically. You don't want to move, maybe it's, a bridge too far to start looking at, okay, my children in Italy versus, the grandparents in Chile or something, it's sort of, maybe there's too many differences there, but that still would be interesting to see. So I think that, I guess my short explanation would be, one is, in order to minimize sort of effects of overgeneralization, one key thing is, sort of splitting your data, not overfitting, and sort of, getting estimates either based on bootstrap samples or, jackknife, something like that, to sort of see what your internal error is, and then using sort of looking at trying to generalize to either the same population or to external population. I think that, yeah, those sort of are, critical and sort of ultimately what you want to be doing anyways, right? You want to be sort of seeing how well do these results generalize.
Sure, and that got the question right on the head. Thank you so much.
No, thank you.
Any other questions?
Hi, this is Wick. I enjoyed your talk, Gary. I'm new to all this, so I get what's called, quote, dumb questions all the time. So at the risk of making it so be it. But are there in any way, are there biomarkers, if I may use that term, for autism characteristics or symptoms? I have 2 kids who are autistic, and by your combining these biomarkers, you're able to see more information. Do you think any idea of any application of this could be done to try to estimate potential impact of environmental chemicals or stressors on autistic children?
Oh, sure. So I think that the general theory that I've been working under is actually work that I did sort of in my graduate program. The concept is data fusion fundamentally, right? You know, you have information from multiple sources, and what you want to do is just combine it, you know, intelligently, obviously, but, you know, combine this information in order to sort of derive more informed conclusions, right? And so what you can do, you know, and so yes, you can totally do this for, you know, a thing that's difficult in autism is that there's multiple phenotypes, right? It's not, you know, it's not really one homogeneous population that you're looking at, right? There's many different subdomains. Some
Long spectrum.
You know, it's a spectrum, but I think that, you know, a spectrum is almost denying the complexity of it, because a spectrum implies that it's, you know, one dimensional. You know, it's really, I think that people have to start thinking about these things in terms of like a surface, right? And it's, you know, there's this complex surface that's going on, and what people are doing, you know, right now is they're just sort of like drawing little circles and like, okay, these people are sort of here and here. And also, you know, people change over time, right? You know, you can move sort of from group to group. It's, you know, there's this temporal aspect. So I would say that yes, you know, in principle, yes, you could totally do this. I think that the, you know, prediction of complex, you know, neurobehavioral issues is, you know, is sort of, in a way, you know, sort of measuring lead exposure is an easy way to, you know, is an easy application. That's sort of more complicated because you sort of have to come into it, you know, with sort of, you know, knowledge of, okay, well, how can I really determine groups? How, you know, what does it mean? You know, how can I evaluate the temporality of it? You know, right, sort of at different developmental stages and stuff like that. But yeah, I think that certainly you would be sort of remiss if you didn't, you know, use sort of multiple cognitive tests, multiple behavioral tests, multiple, you know, many of these tests, and you basically almost want to derive something like a, you know, a vector or some sort of factor, right? That's going to be, okay, well, you have, based on your 14 different tests, you're actually, you know, somewhere in this region or something like that.
Almost like a hypercube in the sense of information, if I'm phrasing that right.
Exactly. Yeah, I think that that's sort of the perfect way to think of it. I think that, you know, it has been for many years, you know, the issue is that, you know, it's very complicated. And so people want to simplify it so they can figure it out. But the problem is that then people become attached to the simplification, and, you know, life is much more complicated. You have
They're making too many projections onto lower dimensional surfaces, but they still need to look at the overall picture.
Exactly. That's 100% right. You know, it's a very complex problem. And I think that only really in the last 5 to 10 years are people really thinking about, okay, it's not just, you know, you have 17 points on this line or something, so therefore we're going to cut the line at 16 points, and they're, you know, okay, you've met the criteria. It's really, you know, okay,
It's gonna be pretty fuzzy.
and stuff like that we have to.
Yeah. Okay. Thank you very much.
You're welcome. Thank you.
I have a question for you, Yuri. You were mentioning preferred biomarkers,
Mm-hmm.
you know, various contaminants. So is that because of the amount of contaminant that goes into that biomarker that is considered preferred?
So I think that the way that people figured out preferred, so, you know, people have been looking at trying to figure out occupational exposure since like the 1800s, and, you know, they're, you know, in terms of how do you come up with something like that. And really, I would say, you know, the last 50 or so years has been sort of the most serious scientific sort of focus on how do we really measure exposure. And a lot of it has really just been trial and error. Like, you know, okay, well, you know, let's see what we can get from this person. Let's see, you know, if we're looking at lead, you know, can we measure lead in nails? Can we measure lead in hair? Can we measure it in blood and saliva? And, then you look at, okay, well, do the levels that I measure correlate or with the, sort of the IQ measures that I have? And it turns out, okay, well, saliva doesn't really do it very well. Okay, but it turns out that, consistently, and so, it's decades of work by different people sort of saying, okay, well, it seems we get the most signal when we use these biomarkers. So with lead, they're finding the most with blood and bone. Bone is more sort of cumulative. So it's like, really just this average of sort of your lifetime of exposure. And another thing that people have started using, I think, since like the 70s or so is animal models. So they'll basically dose, rats or mice or something with specific levels of, cadmium or lead or something like that. And then they'll look at, okay, what's the level of, can we measure it in blood or, urine or hair and something like that. And then, we know exactly how much we gave them. So if, do these levels really match up? And so that's been a lot, I would say, sort of to almost confirmatory, like people have seen it, in practice in terms of where they detected, significant correlations where they didn't. But the animal models sort of really almost confirmed it. The problem is that, there are thousands of new chemicals that they come up with, it feels like daily, but, and so you can't really just run animal studies like on all of these chemicals. So I think that part of the motivation for this work is, can we, come up with something that can be a little bit faster than running these, controlled trials on animal.
All right, thank you very much. Any
Thank
other
you.
questions for Yuri? Okay, well, thank you very much.
Thank you. Yeah, everyone, thank you for coming. Have a great rest of your day.